Okay. Warm greetings to all Einstein Toolkit aficionado. I'm sorry I can't be there. Thank you for allowing me to present my work on multi-messenger signals from magnetized binary neutron star mergers. I work at Marshall University. Okay, so without further ado, let's look into binary evolution. We know that there are billions of neutron stars in our galaxy. Only 2,800 are pulsars and can be known, but only 20 are in neutron star systems. In the system, one star will evolve faster, and when the companion evolves, gets through a recycled phase. That means that the mass of the first star is heavier, and the gravitational and the magnetic field of the second star is larger. Detection of collision of binary neutron stars was GW 17017 that everybody knows, and started the field of multi-messenger astronomy, and was quoted as the golden binary and opened the golden age for neutron star research. Until now, over 90 gravitational waves were detected, but most of them from binary black holes. In fact, only one other was detected, but no clear electromagnetic counterparts were found, neither a jet nor an optical afterglow. So my motivation is to look into those detections and see if I can answer some of those questions, or at least investigate. One of them is, what can the gravitational waves emitted tell about the equation of state? What's the correlation between the amplification of the magnetic field during collision and the emission of the electromagnetic counterparts? The holy grail of this kind of research is to find out when and how does the jet emerge. What about the ejecta? What is the amount and composition of the ejecta, and how it's linked to the production of heavy elements and kilonova emission? What is the nature and fate of the remnants? And of course, what new physics can we discover? Let's explore this to numerical relativity simulation, namely with Einstein Toolkit, that offers multi-physics modeling. It allows us to evolve dynamic space-time, takes care of gauge and singularities, also evolves matter with numerical capturing methods for instabilities, shocks, discontinuity, has conservative and primitive reconstruction implemented, and the realistic equation of state. It does not have yet general relativistic radiation transport, neutron leakage scheme, conversion of electromagnetic flux to electromagnetic spectrum, so there's things that can be improved. The computational grid that I'm choosing is a cube of 1,000 kilometer cube, 6 levels of refinement. The maximum refinement is coarse, indeed, only 250 meters. Those are preliminary runs. And the central grid is 100 kilometer cube is refined with this refinement. As initial data, I use Lorraine, which is freely available. Unfortunately, it gives wrong results for unequal mass binaries. So my intention is to simulate unequal mass binaries. But there is freely available Lorraine initial data. And here you see on the right comparison between the result given by Lorraine for different mass ratio and by the one at this RIT link. So this is AP4 equation of state. An advantage for Lorraine is can generate initial data for mixed equation of state, but it still needs to be implemented in Einstein Toolkit. Lorraine offers two types of equation of state. So I picked as initial data, I picked 4 equations of state. MPA1, which is a relativistic hard equation of state, AP4, which is a soft one, and two equation of states which are basically mild AP3 and SLI. And you can see that the second mass on the binary is pretty much constant, 1.53, or gravitational mass of 1.34. The first mass in the binary starts at 1.78 and goes to 2.31, with the mass ratios 116, 133, and 1.50. Coordinate separation is 50 kilometers, and the chirp mass is between 129 and 143. 143 is a characteristic for the GW 190425. You see that the radius is large for MPA1, and which is a stiff equation of state, and is smaller for SLI and AP4. So SLI is a soft equation of state. When we start with the evolution, in here I present clockwise AP3, AP4, MPA1, and SLI. For the mass ratios 116, mass is 1.8 and 1.55, chirp mass 129, and the time, this is the first is initial time, and then clockwise co-time 540, 60, 90. I use a seed internal poloidal magnetic field in which the heavy neutron star has 10 to the 8 Gauss and the lighter neutron star 10 to the 14 Gauss. Okay, but we see that the stars begin to separate. Is this a magnetic repulsion? And possibly I put the magnetic fields oriented parallel. So we see that the heavy stars, neither MPA1, neither AP4 or AP4 end up actually coming together. So this is a further study. And then AP3 before MPA1 of 1.16 mass ratio do collide. AP3 and AP4 form a black hole and the run stops, while MPA1 evolves for a very long time, but it acquires a kick, and the kick pushes the star out of the grid domain. So what is to be done? Shall we hand it to another grid, or is it feasible to get such a
1 minute,
large
please
grid?
conclude.
Analyzing outflow, we see that MPA4 has the least, the stiff equation state has the least outflow, which is expected. We see in the logarithmic scale that the outflow is similar. We see that the heavier ones have a very sharp peak, but this is basically the grid sees the smaller star as the outflow because it's ejected.
30 seconds, please conclude.
As the energy, would be interesting to see if the outflow has enough energy to interact with the interstellar medium to generate electromagnetic counterparts, and the most promising is AP4, who has higher energy. We've seen here for mass, for different mass ratio, for the masses, the binary in which the masses are mass ratio is smaller, have more ejecta. And in conclusion, detected neutron star mergers left important unanswered questions, carried out numerical simulations of realistic binary neutron stars. I use publicly available, everything is publicly available. I use basically GR Hydro. This is a work in progress. More studies are required to determine what is the role played by the equation of state and the magnetic field and the ejecta during the merger. Thank you. I'll take questions now.
All right, let's thank Maria. Questions? Yes.
Can you elaborate more on, you said the asymmetric initial data wasn't working, but you said asymmetric results?
The question is, can you elaborate on the fact that asymmetric initial data was not working in Lorraine, but you still showed asymmetric results?
Yeah, so what I said is that Lorraine, if you go on and use the Lorraine as it is packaged, it doesn't work, but there is freely available Lorraine initial data in the RET webpage. So that's where I ended up taking the initial data for unequal mass binaries.
So you couldn't generate it yourself, but you found someone that did. That's the answer.
Well, I could generate myself, but Lorraine has a bug in it, and it's not the one that is publicly available is not fixed.
I see. Okay. Unfortunately, we do not have more time for questions. So thank Maria again.